And now for part 2. Welcome back. How to interpret pushing undoing operations. It sounds slightly philosophical. However, consider, if all the parameters are satisfied, then the inverse can undo anything, thus reversing a position to a new position, or back to its original state. Now that's something we can work with. So let's further clarify. A function must be injective, sometimes referred to as one-to-one, to have an inverse. This means no two different inputs produce the same output, unlike in our non-example in the previous video. Then we think a discussion of the domain, codomain, and range of a function would help the overall walkthrough. The domain, the set of all input values. The codomain, the set into which output values are constrained to fall. The range, the set of all actual output values. First things first, the domain of X in mathematics is the set of all the possible input values for which a function is defined and produces a real number output. Think of it as the set of all numbers you can plug into a function without the function breaking or giving an undefined result, such as dividing by 0 or taking the square root of a negative number, which would involve using imaginary numbers. For example, inputting a decimal number in our odd-even function will give an undefined result. Generally speaking, the expression in the blue box is something you might come across for a good reason, as it serves to define a function. Recall the function from the previous video, which is f of x equals if x is odd, input into x plus 1. If x is even, input into x, with the following parameters in the blue boxes. In this discussion, we're carrying the function over with some adjustments to the parameters. Named f for our odd-even function, which takes numbers from the set of natural numbers, denoted by capital N, as inputs, and produces natural numbers as outputs. In other words, for any natural number x that you input into the function f, the corresponding output, f of x, will also be a natural number. So f is the name of the function. The colon just serves to separate the function's name from its domain, and codomain, the capital N on the left side, represents the domain of the function, the set of all possible input values. The arrow indicates a mapping from the domain to the codomain. The capital E on the right side represents the codomain of the function, the set of all possible output values, which is true for the function, which just returns even natural numbers. Briefly, in mathematics, a mapping is just another name for a function, a rule that associates every element of a set, the domain, with exactly one element of another set, the codomain or range. The term mapping could be considered like a visual, like referring to a max as a crest or a min as a trough, which emphasizes the process of this association, similar to how a geographical map connects points on the Earth's surface to a flat sheet of paper. Accordingly, the shaded area is the domain, the set of natural numbers. But then we can further restrict the domain by writing the closed interval, the integers 1 through 6, the small d really being a subset of capital D. See that? Next, a codomain can be any set that contains the possible values of the function, which means any authors have a choice when stating a codomain, which has a practical purpose of preparing a reader's expectations, such as the function's potential outputs and behavior. At first thought, The codomain seems redundant, because why can't we just have range, which are the only possible outputs? However, there's at least two arguments the codomain has a significant purpose beyond the range. First, it's considered as a part of a function's formal definition, such as it defines the function's target space. Second, a codomain allows for identification properties, like the characteristic of surjectivity, which gives context to a surjective function. More on that coming up, though. And so, the codomain is the set of possible outputs, providing any writer, which includes us, the possibility to convey a broader context of a function's behavior and revealing aspects that the range alone does not. What do you think? We think it's a good argument because it applies to our current example, as it's articulating the set of possible outputs of our odd, even function, hence conveys it having a broader perspective compared to its restricted range. Accordingly, the codomain is the entire shaded region on the right, while the range is the set of the actual outputs, which is probably what people are most familiar with. For our function, we have the restricted range, which are the integers 2, 4, and 6, the set R in the yellow box. So what do you think? The way it's written, could that represent a better description of the function's behavior? Even if the function with its restricted range is describing something in nature or a mechanical process. The way the function is written, it can apply the set of natural numbers, which will return the set of even numbers. It returns the set of even numbers because, technically, duplicates in a set are not counted, as a duplicate element is not considered to be in the set multiple times. Lastly, observe the red box. Sometimes the number 0 is included in the natural numbers. However, in this case, we are not including 0.